Hello, this is Ulrich Ginnig with a short tutorial video on light and on photons. Most of the things that you will hear about here you have probably heard before in your high school physics lecture or in the lecture here at the university on physics or an earlier part of an analytics course. So this is just a quick recap of the most important facts about light and photons that will be used in the microscopy part of this course. So here we have the visible spectrum of light. It ranges from about 400 nanometers wavelengths to about 700 nanometers wavelength. 400 nanometers is sort of like deep blue purplish color, and towards 700 nanometers it's red. And if we go even further towards the blue side, we continue here, we end up in the ultraviolet part of the portion. And if we move further here away from the red, we end up in the infrared part of the spectrum. So light, we can think of light as an electromagnetic wave. Okay, so that's the wave nature of light. And the way to think about this is that we have an electric field shown here in blue that oscillates. And this oscillation of the electric field generates a magnetic field, which is perpendicular to the electric field, which also oscillates, and the oscillating magnetic field in turn regenerates the electric field. So the electric field and the magnetic field, they travel along together as a wave. What is also another way of thinking about light is to think about it as a particle, in particular to think about light as what you call a photon. Okay. So photons are the elementary particles of light. And we very often, when we draw photons, we draw them sort of as a short squiggly line with an arrow at the tip. And that represents sort of one photon particle moving along. The wavelength of the photon gives the energy that is contained in the photon. And the reason it makes sense to think about light in terms of photons as particles is that the energy that's contained in light is sort of absorbed one photon at a time. So the energy that's contained in one photon cannot be split or partially absorbed. If a photon is absorbed, all of the energy contained in that photon is absorbed into the molecule, and the energy is only absorbed if the transition in that molecule has exactly that energy that is contained in the photon. Okay. So to give you an idea about what kind of energies we're talking about, let's review the energy contained in a photon. So the energy of a photon equals the Planck constant. That's sort of something you should know from sort of your physics, basic physics class, times the frequency nu of the oscillation of that electric field. So typically we don't actually don't think or talk about the wavelength of photons in terms of the frequency of the oscillation, but we talk in actual wavelength, which is lambda, which is given in nanometers. Okay, so we need to convert this, and there we know that the speed of light is the frequency, or is the wavelength lambda times the frequency of the oscillation. Okay, and so that allows us then to make this substitution here for nu, which is that the energy of the photon is h times the speed of light, the constant speed of light, and the wavelength. Okay, so we now have this equation here for the energy of a photon, where we just have two constants, the Planck constant and the speed of light. and then we have the wavelength of the photon. And what is important to realize here that the wavelength is in the denominator of our equation, which means that the shorter the wavelength, the farther we're towards the blue, the higher the energy, and the longer the wavelength, the lower is the energy. So what kind of energies are we actually talking about? If we take the photon energy of an individual photon and we multiply that times Avogadro's number, then we get the energy for a mole of photons. That's sort of a good quantity to think about for us as biochemically minded people, because we think of bonding energies and reaction energies, activation energies in terms of kcals per mole. Okay, so for light that has 450 nanometers wavelength, we can use this equation here and multiply it by Avogadro's number afterwards to get the energy for a mole of photons for 450 nanometers is 63 kcals per mole. And 680 nanometers, which is sort of like towards the starting edge of the infrared, nice deep red light, has 42 kcals per mole. Okay, so let's compare this to other energies that we run across in biology or biochemistry. So the first one is the energy of breaking bonds in an organic molecule. So we have a carbon-carbon bond, and then you would have here R1 and then R2, and you have two hydrogen atoms bound to here. And the energy that it takes to just rupture this bond, to rip this apart, that is on the order of about 100 kcal per mole. Oops. Okay, so the energy is actually in that we have in photons that are absorbed is sort of a similar order. It's smaller than the energy to just rip apart the bond, but it's getting fairly close. So that should give you the idea that whenever you absorb a photon in an organic molecule, there's the potential for chemical rearrangements. Okay, so we're on that order of energy. It's not so much energy that it will immediately rip apart the molecule, but we're close to that realm. Another energy that is useful to think about is thermal energy. Okay, so if let's say we have a water molecule and you have one oxygen and two hydrogen atoms, then thermal energy will mean that this molecule is constantly jiggling, vibrating, moving about. You have translational energy, you have vibrational energy from these bonds moving, you have rotational energy, and so on. Okay, and these molecular motion energies at room temperature, they're on the order of about 1 kcal. Okay, so per mole. So that is substantially smaller than the energy contained in a photon.